Kia ora Year 13. This is the second part of question 1 of last year's distributions paper. So this question goes from achieved up to excellence, and it's all about cars. Right, so it's estimated that 13% of the cars driven on New Zealand roads are red. Suppose that the colours of the next 7 cars that pass in an opposite lane are observed. Use an appropriate distribution model to calculate the probability that at least 2 of the 7 cars are red. So at least means greater than or equal to. So it should be pretty clear by now, 2 days before the exam, that we are dealing with a binomial model. So we need to state the model and then state its parameters. So n is the first parameter, the number of cars. N is 7. P is going to equal 0.13. Alright, so we want to find the probability that at least 2 of the 7 cars are red. Now I'm assuming that if you're watching this and you're doing level 3 stats, you've got a graphics calculator. So I'm not going to do all of this with a table. If you are doing it with a table, then I'm sure that you have learnt that thoroughly in class by now. But to work with the graphics calculator, remember we have to work with the lower tail to use BCD on our calculator. If you find this tricky, think about the possible things that can happen. So there's 0, 1, 2, 3, 4, 5, 6 or 7. Right, so draw them as open circles. We could label them up to 7. And we want the probability that there are at least 2 cars are red. Right, so I'm colouring in these dots because sometimes if you are stressed out and you're trying to remember what you want to include or not, the dot thing can help you. So we're looking for the red dots in the probability, which means I'm looking for 0 and 1 not in the probability, which is where that comes from. So the probability works out to be, what have we got, 1 minus 0.77, I think I got 0.7719, so that probability is equal to 0.2281. Now I would usually go to 4 decimal places, so that's what I would put for that. So that's the first question, to calculate a probability, and that is a little achieved question. Not surprisingly, we are then asked to talk about why we think this is a good model. So that's on the next slide. Right, justify your selection of a probability distribution model. So I think binomial is suitable because, right, and then we roll out our 4 conditions and we make sure we write about them in context. So start with the easiest ones. Actually, all you had to do was talk about 2 of the conditions. So if you're lucky enough for that to be the case, start with the easiest 2. The first one is we've got a fixed number of trials. Now, it's not enough to say that. That doesn't mean anything. We have to say 7 cars. Next thing is that we've got 2 outcomes only, and they are red or not red. Okay, you will get no credit if you don't put it in context. Okay, so make sure you do. So you have to say red, I'll put it back in, red or not red. So they're the easiest 2, but the other 2 are pretty straightforward here too. I'll put them on a new slide. Right, we've got a constant probability or fixed probability of what we call success. Success here is being a red car, and that is 13% red. And then we've got events are independent. And what that means here is that chance that a car is red shouldn't or doesn't depend on the colour of the last car. Right, hopefully guys you can see why I haven't done as many stats videos. I'm trying to give you the sense of what you've got to write, but it's pretty boring watching me write that. Please make sure that it's in context, because that is what we're after for a good answer here, right? It's not enough just to write the 4 conditions. Okay, so that's bad. You've got to be talking about why the situation fits this distribution. Okay, so we're up to merit. Now we're going to do the last little bit, which is some excellence stuff. Alright, for n number of cars that pass in an opposite lane, the probability that at least one is red is 0.965. So we've got probability that x is greater than or equal to 1, 0.965. And we need to figure out how many cars that was. So when we're working with binomial problems like this, it's much better always to work with the low end of the distribution, because in this case we don't know how many dots we've got. If we think back to how we drew the dots for the 7 cars, well, that's my 7, but here this is going to go on, and we don't know what that is. So to solve problems, we can't be working with that end, but we can say that the probability that x is equal to 0 must equal 1 minus 0.965, which is 0.035. Okay, so the probability that x equals 0 is 0.035. Now you can think about the binomial formula, but even better, you can just think about a long, long tree diagram. So to have no red cars out of n, we must be multiplying down one branch of tree and ending up with 0.035. So no red cars means that all of the cars are not red. So the probability of not red is equal to 0.87. So what we're working with is 0.87 times itself for all n trials. In other words, 0.87 to the power of n is equal to 0.035. Now we're going to take logs of both sides. Doesn't matter what base we use for the log. You can use, if you're doing the log button on your calculator, of course it's base 10. You could use the natural log as well. It's not going to make any difference. Not going to go into why right now. But here we're going to use our log rules. And we're going to get n log of 0.87 is equal to log of 0.035. I'll finish that off on the next slide. Okay, so what do we get? Well, we get n is equal to log of 0.035 over the log of 0.87, and that works out to be 24 point something. Now it's just a little bit over 1. Just trying to find my working here. Let me see what I got. Yeah, I got 24.07. So it's fine to say that we would need to have that probability. We'd need to have 24, or we could round up and say we'd need to have 25 cars to have an 87% chance that at least one is red. Okay, so this is your answer, and then this is your answer in context. Right, I'll be back with question 2 later on.